Hi, friends. Our focus for this discussion is going to be on how to manage trace mineral applications. Over the last couple of years, as we have been speaking about the need to have trace minerals in the correct oxidation state, as we've been learning about redox from Olivier Husson, and the capacity of biology to convert minerals in the soil, trace minerals in the soil, to different oxidation states, there have been more and more questions about how to correctly manage these trace mineral applications. Also, as we have learned how some types of metrics of measurements, some types of laboratory analysis don't correlate with actual field results. So there's been the potential to create some confusion. I've received a lot of questions about how to manage trace mineral applications well. And my intent and hope is to answer all those questions here as succinctly and coherently as possible with the different pieces that I have learned over the last couple of years. And who knows, as we continue learning in a few years, then some of this information might change as well, but we will cross that bridge as we get there. When we think about trace mineral deficiencies, one of the pieces that I don't have on this slide deck is observing the nutritional deficiencies visually. And I will speak to that a little bit as we go through this. The reason I didn't include this is there's two reasons. One is you want to have crops that have such strong nutritional integrity that you never see these visual deficiencies showing up in the first place. If the deficiency is so pronounced and so severe that it is showing up visually, you've already had a very significant impact on the crop's yield potential. So that is part one. And then part two is that while these nutritional deficiencies of, let's say, of a manganese deficiency, the symptoms of that are fairly universal across, as far as I know, all crop types, at least those that I have experience with and I'm familiar with, and even non-crop plants such as weeds and so forth. But I do also know that for some of these trace mineral deficiencies, indicators and symptoms, there is individual variability within different crops, and some genetics show them up a little bit differently than others. So that's something that I wanted to point out as well. When we think about applying trace minerals, the first piece, of course, that so many of us are now aware of, and at least for myself, I was not aware of this to this degree 8 or 9 years ago, is the need to apply the correct oxidation state. Now, the need to apply the correct oxidation state for optimum plant performance is not true for boron. It's not true for zinc. And my understanding is that it's also not the case for molybdenum. But for all of the other trace minerals, manganese, iron, copper, cobalt, and selenium, and there's obviously a much longer list than this that we could speak about. We could also speak about nickel and iodine and vanadium and rhodium and some of those other elements. But for this conversation, we'll be focusing just on the primary, on the major trace minerals or micronutrients that we often think about managing and that we need to manage well. So these others that I mentioned can have different oxidation states. Iron can be Fe with a double positive, triple positive, or quadruple positive. And when they are in the oxidized form, they behave differently in soil microbial populations and within plants. And for some of these, with manganese, for example, plants don't have the capacity to absorb oxidized manganese. In the case of iron, they can absorb it, but they can't use it. So it's very important for the plants for all these trace minerals, iron, manganese, copper, cobalt, and selenium, the optimum is for plants to absorb them in the reduced form rather than in the oxidized form. I'm not going to get into the chemistry and biochemistry of what redox is and understanding different oxidation states. If you want to dig into that a bit more deeply, I highly recommend Olivier Husson's free course on the Academy, academy.regen.ag. You can find that 6-hour course and you will absolutely love it. Incredible information about understanding redox in plants and soils and how it impacts nutrition. So now the question becomes, how can we have a product that is in the reduced form and remains in the reduced form. Those are two very different things. So the first is that we have to get the nutrients in the reduced form, and quite frankly, it is difficult to buy minerals in a bag that are in the reduced form. If you purchase iron oxide, for example, all the oxides, all the trace mineral oxides, it is evident in the name itself, by the presence of having an oxide, that these nutrients, these minerals, are in the oxidized form. When we purchase sulfates, such as iron or manganese sulfate or copper sulfate, the sulfates contain the elemental expression is SO4, so we have 4 components of oxygen, which also expresses that the sulfates generally are also oxidized. So these first need to be converted, so disassociated from their oxidizing components in a solution, and then converted to the reduced form, and then stabilized so that they stay in the reduced form. And when you get into the biochemistry of redox reactions, there's obviously some proprietary information here, because in our work at Advancing Eco-Agriculture, we have our rebound line of trace minerals, which are developed in this way to be reduced and to remain stable in the reduced form. So biochemists will be able to help you figure this out if you don't have access to those materials, to AEA materials, if you're overseas or something like that. But the key element is that they need to be converted to the reduced form and then chelated so that they stay in the reduced form. And this is particularly relevant for foliar applications and also for in-furrow applications at planting. Chelation is not optional. They need to be chelated, and there are 2 reasons for why chelation is not optional. The first is that if you have a reduced trace mineral ion, let's say manganese for the sake of discussion, if you have reduced manganese in the spray tank, you spray it out through a nozzle, it lands on the leaf surface, a small droplet dries on the leaf surface, and as it dries, it now is exposed to oxygen in the air, and it can become oxidized very, very quickly. So to prevent oxidation on the leaf surface, these trace minerals need to be chelated. And then also, once they have been absorbed by the plant, chelation will improve absorption by the plant itself, which is really important as well. And then there are different chelation agents have different effects, but the best chelation agents are those that also provide phloem mobility. They allow these trace mineral chelates to move around inside the plant. So you spray it onto the leaf, and it can move from the leaf into the fruit or down into the root system. And this is very important if we want to use trace minerals to provide disease resistance, for example. So it is known that when we have abundant manganese in the root system, that can provide fusarium resistance, because it gives the plant the materials that it needs to produce corking in the cells and to insulate off and to create a barrier to prevent wherever an infection has occurred from propagating through the rest of the plant. Those reactions are dependent on manganese. If we want to move manganese from the leaf down into the root system to have this effect, it needs to be chelated. Manganese sulfate applications will not provide any results because it's not chelated and doesn't move down into the root system. So the need for chelation is particularly critical for foliar applications. It is also critical for in-furrow applications at planting. And the only case in which I would suggest that chelation is not needed is when we are making soil amendment type applications. And the soil amendment type applications are only appropriate for some trace minerals in some situations. So let's get into that. Looking at each of these minerals one-on-one, starting with boron, I wanted to kind of provide an overview of how we see the different lab reports correlating with actual field results. We find that soil analysis are generally accurate, and that tissue analysis are generally inaccurate, and the inaccuracy can vary depending on the speed of plant growth. The sap analysis we find to be the most accurate, And we do find that for boron, soil amendment applications of boron are appropriate. It is the least expensive and the most efficient and effective generally to put on boron applications for an entire crop year in advance, unless we live in an environment where we have extremely high rainfall and it can leach out. So all the various different forms of boron work well. This is not one of the elements where we have to be concerned about different oxidation states. Solubor or disodium octaborate tetrahydrate has different brand names, different trade names, but it is the most soluble, 20.5% boron content, the easiest to dissolve and to apply. The form of boron that plants absorb the most easily is boric acid, and it is also the easiest one to produce toxic effects with boron. We often, many growers and many companies chose not to use boric acid for that reason, because of concerns about toxicity effects. And then, of course, if you want to do a dry broadcast application, you can use any of the dry 10% boron granular products. My preference for a soil amendment application is to spray it on rather than broadcast spread it because of distribution. We get much better distribution, much more uniform and much more even distribution if we spray it onto the soil rather than broadcast it, and we end up with one pellet over here, another pellet 3 feet away. Our typical recommendations are for a ½ pound of actual boron per acre. So this is not a boron product as in a 10% product, but 0.5 pounds of actual boron per acre for each 10 inches of annual water application from rainfall. So if we are here in the eastern United States where we get 40 inches of rainfall a year, we know that that 40 inches of rainfall has the capacity to leach about 2 pounds of boron out of our soil profile, because boron is an anion just like nitrogen and sulfur and leaches out through our system fairly easily. Until we develop high organic matter content soils that hold the boron stably with a strong anion exchange, and then once we have a strong anion exchange capacity, we often find that we don't need to continue these repeat boron applications. But until we get to that point, we routinely recommend boron as an annual application, as a soil amendment type application. And then we continue those applications until our soil report shows us that our boron levels are being maintained stably at 3 parts per million in the soil profile. At that point, we back off applications and don't continue any further applications into the future unless either sap analysis or soil analysis shows that they're dropping off again for some reason. In a truly regenerative system, they should remain fairly stable, and we shouldn't see that drop off into the future. For foliar applications, we make foliar applications of boron on many, many different crops. And the only consideration to really think about is that we need to consider that we have adequate calcium levels, particularly for the sensitive crops. The symptoms of a boron excess are the symptoms of a calcium deficiency. It is possible, if you have excess of boron showing up for any reason, simply put on a foliar application of calcium and it will fix the problem. Depending on how severe the problem is and the rate of plant growth and the context, it can reverse the symptoms, the visual symptoms, anywhere from 48 to 72 hours. Sometimes it takes a bit longer, sometimes a bit less, but that's a reasonable window to expect a calcium application to fix a boron toxicity symptom. Next, we look at cobalt. Soil reports are generally accurate. Tissue reports seem to be generally accurate. Cobalt is an interesting element. I read somewhere or learned that cobalt tends to concentrate in the root system, in the growing root tips. I do recall now, an agronomist from California shared that when you do a root analysis, in addition to a tissue analysis, you will quickly discover that 90% of the cobalt within a plant is in the root system, not in the leaves. And I find that to be really interesting because of its association with cytokinin synthesis and inhibiting ethylene synthesis. So lots of interesting relationships that happen with cobalt. Sap analysis also is very accurate. And cobalt is one of these elements where it does exist in the soil in different oxidation states. But we do find good crop responses and good biology responses from cobalt applications to the soil in the form of cobalt sulfate. And my hypothesis, I don't know this for certain, but my hypothesis is the reason this is the case is because cobalt is so critical for soil biology. Soil biology has such an extremely high requirement for cobalt to form vitamin B12, cyanocobalamin or methylcobalamin, that when cobalt is applied, it is mostly very rapidly consumed by the soil microbial community, and thus it doesn't exist in the soil profile in the oxidized state very long at all. Again, because of application rates, typically we're looking at desired levels. Depends on what type of soil analysis you're running. Is it MELIC 3 or DTPA type extraction? But typically looking at desired values in the neighborhood of 0.5 to 1 part per million. And our preference, because of soil variability, is to use foliar applications to make sure that we have enough during the growing season. When we look at copper, we find that a tissue analysis often doesn't actually correlate. It's somewhat inaccurate. SAP analysis is the most accurate. For those of you who listen to these webinars and listen to me a lot, you know that we are big advocates of SAP analysis because of its accuracy in these regards. And we very seldom, but occasionally, recommend soil applications of copper in the form of copper sulfate. The conditions where we would make such a recommendation would usually be on very light sandy soils that do not have copper in the geological profile, and where copper levels are extremely low, and where copper levels are not being applied for bacterial control in the form of bacterial copper sprays and so forth. In these types of situations and scenarios, we would often recommend putting on copper sulfate sprayed onto the soil, again, for best distribution, uniform distribution. And it's important, everyone focuses on the downside of copper application in the soil, which is significant. Copper levels in the soil can inhibit and do inhibit microbial populations. As the levels get higher and higher, they slow down the microbial populations more and more until you cross a threshold of about 30 parts per million. And from what I have learned from colleagues, I haven't experienced this myself very often, but from what I have learned from others is that when you cross the threshold of 30 parts per million, soil biology becomes severely compromised very quickly. And our typical recommendations in the consulting work that we do at Advancing Ecoagriculture is to mostly focus on foliar applications, and only very occasionally do we make a soil application recommendation. Now we get to the fun ones, the really fun ones. Iron. The soil report is grossly inaccurate. It has zero bearing on reality with what's actually happening in the soil context. It's a very significant statement to make, but one that we have very much observed to be true. We know that the Earth's crust is approximately 4% iron. There is no shortage of iron in most of our soil profiles, and there should be no need to ever add iron to our soils. However, the majority of the iron that is in our soil profile is in the oxidized form, in a form that plants can absorb but not use. And because they can absorb it but not use it, this also makes the tissue analysis, dry matter-based tissue analysis, completely inaccurate. There is no correlation between the iron report on a tissue analysis report, the measured iron content, and the iron sufficiency of the plant. In fact, just the opposite. Many times when we pull soil analysis or tissue analysis on many mineral soils in temperate regions around the world, we find that the soil analysis shows we have excessive iron, and the tissue analysis shows that we have excessive iron. And yet, the crop is showing us iron deficiencies. I should qualify and clarify that statement. Most plants don't show iron deficiencies because they are covered up with excessive nitrogen. So when you have a plant that has an abundance of nitrogen, that abundance of nitrogen will cover up the iron deficiencies so that you don't see it visually, but it is still there and it's still affecting plant performance. once you begin managing plants a bit differently and they no longer have the excess of nitrogen that is causing all types of other plant health problems, then you can go out, put on a foliar application of a reduced iron, and see what happens. You can paint your name in the grass, and you'll be able to see your name showing up in the grass in a matter of a few days. You had this very pronounced iron response, even when the tissue analysis shows that you have abundant levels of iron within the plant. The problem is that the iron within the plant is not physiologically active. In fact, we have worked with a number of growers, farmers who is particularly true of forage producers, people who are growing hay or forages for livestock and dairy, for example. When they're conducting a forage analysis and a sap analysis side by side, they're using the sap analysis to manage applications of nutrients, foliar applications to try to produce the highest forage quality possible. And at the same time, they're doing a forage analysis, not so much necessarily for the manganese and iron and zinc content as to measure the forage protein content and carbohydrate profile and fat profile and so forth, digestibility, etc. What we have observed, but essentially then the mineral profile of a forage analysis generally is a wet chemistry analysis with the labs that our growers use. It can also be NIR, near infrared, but we generally recommend the wet chemistry analysis. And so we have a dry matter-based tissue analysis that's a wet chemistry, very accurate, compared to a sap analysis. And we've observed some very interesting correlations with iron. When growers, typically, the forage analysis will show excessive levels of iron, 40, 60 to 80 to 100 parts per million or more. And the sap analysis shows deficient levels of iron. The sap analysis, and let me be clear, I'm not a laboratory technician. I don't understand the differences in the processes. I don't understand why the sap analysis doesn't show the oxidized form of iron like the tissue analysis does. I don't know why the differences in those assays, but I know from a lot of experience that it's very real and it shows up. So on these forage tests, we'd have very high iron levels, and the sap test, very low iron levels. Then the farmer begins putting on foliar applications of iron as a result of sap analysis showing low, and the iron levels on the sap analysis went up very, very quickly. And as the iron on the sap analysis levels increased, the iron on the forage analysis decreased, and it went down to be in the vicinity of the desired range. So I found this really intriguing. My interpretation of that is my hypothesis. Again, I haven't deeply dived into all the mechanisms, but my hypothesis is that it seems as if though once the plant is getting iron in the correct form that is physiologically active, it no longer continues to consume excessive iron in the wrong form from the soil profile. So the reason it seems as if though these plants that are getting oxidized iron from the soil continue to consume it and absorb it because they recognize that they're iron deficient and they need more, and they're trying to get everything they can in order to get it in the right state. And this is a separate conversation for another time, but these high concentrations of iron lead directly to a plant that is not functioning as well as an antenna, lower absorption of manganese and zinc and these other trace mineral metals, and significantly increases disease susceptibility. So these excessive levels of iron in the wrong form are a significant challenge from a disease resistance perspective. And also, something we need to think about for organic certification is that in order to apply these trace minerals, we need to have a documented deficiency. And with a tissue analysis or a forage analysis or a soil analysis, in most soils in North America and around the world, you will constantly have documented excesses rather than deficiencies because the extraction is extracting things that the plant can't actually use. So for these reasons, we use sap analysis as well, and we actually use sap analysis also to describe a documented deficiency for the growers that we work with. So because of iron being so abundant in our soil profile, we practically never recommend a soil application. And when we do, it would only be in soils with no iron in the geological profile. Again, perhaps very sandy soils that are fundamentally beach sand. And instead, we focus on developing biology to convert the iron in the soil profile from the oxidized to the reduced form. And as I described here, foliar application is what we prefer and what we focus on. And because of this oxidation imbalance that is present in many aerated soils and in many tilled soils, the crops that are grown in a lot of mineral soils are almost universally deficient. And this is also true in soils that have lots of fertilizer applications, nitrates, limestone, and so forth, all have an oxidizing effect. And the key here is not to apply more to the soil, but to change the soil's microbial profile so that we release the iron that is already present. We shouldn't need to buy any more. There's a similar case with manganese, with some slight differences. Manganese and iron are not quite the same. What we have observed is that the soil report is somewhat accurate at showing what is available for plant absorption. The tissue report is grossly inaccurate, does not correlate to, well, let me clarify. It is very common for manganese applications to be made, foliar applications, to be sprayed on the plant and remain on the leaf surface, but not actually be absorbed into the leaf. And when this occurs, it makes a tissue analysis extremely inaccurate because you can't really wash, and what we've observed and experienced is that you can't really wash a manganese residue off the leaf surface very easily. So it shows up on the tissue analysis, but it has no bearing on the quantity of manganese the plant has actually absorbed. Sap analysis, again, we find to be the most accurate. And I don't need to get into all the history and some of the stories that we experienced, but when we first started using sap analysis, it was very common for us to make recommendations for manganese sulfate foliars, because we would put on manganese sulfate as a foliar, we'd collect the tissue analysis, and the needle moved very quickly. We thought we were making a difference. When we started using sap analysis, we quickly learned that we were not making a difference. The needle was not moving. And so we did find that the sap analysis did not extract the nutrients that were on the leaf surface. So when we look at the applications, the types that we recommend, we almost never recommend manganese as a soil application for the same reasons as iron. Many mineral soils, and this is casting a really broad blanket, lots of generalities. You can get this tested and measured and should, but many soils contain manganese in the upper 6 inches in the range of 200 to 400 pounds per acre, sometimes more, sometimes a little bit less, but certainly high enough that you very seldom should need to add additional manganese to the profile. Similar to iron, the objective should be to stimulate biology to extract the manganese that is already present in the soil mineral matrix and make it available to plants. And the only cases where we would really consider making recommendations for manganese applications would be in those soils that don't have this manganese base in the geological profile. Muck soils, for example, or very sandy soils. And for all the reasons that I've already described, we recommend lots of foliar applications, and we see a lot of deficiencies. The manganese deficiency signals are almost universal, and I've described them before, but a manganese deficiency is when the veins of a leaf are lighter in color than the area between the veins. At the very least, they should be uniform. They should be exactly the same color, a uniform dark green. But when the veins themselves are lighter than the area between the veins, that's a signal of a very slight manganese deficiency. And that signal is almost universal on weeds, on grasses, on grains, because of the ways that we have managed our soil profiles, except for those crops which are grown in very reduced environments that have an abundance of manganese availability. like cranberries and blueberries, for example. They often don't exhibit signs of manganese deficiency because they're grown in a very reduced environment, in some cases, not in all cases. But they can be grown in very reduced environments that have abundant manganese availability, and then they do not show those symptoms. When we look at molybdenum, soil reports, tissue reports are both somewhat accurate. Molybdenum is an anion like nitrate, nitrogen, and sulfur and boron, so it leaches out of the soil profile. It's extremely available at high pHs, and we occasionally recommend it to be applied to soil. And again, we're looking at very small amounts, grams or ounces per acre, and we really prefer to see it applied as a foliar application because then we know that it gets into the rhizosphere. And this is actually an important point, is when you consider a soil correction, particularly in a perennial environment where you're growing, let's say, an orchard or grasses, if you broadcast a soil amendment application onto the soil surface, then over a period of time, it will be acted upon by biology and absorbed by the plant and moved throughout the entire plant structure, hopefully. And this can be a process that takes weeks to months, depending on the context, moisture conditions, and microbial activity, and so forth. When you put on a foliar application, it can be immediately absorbed by the plant and distributed throughout the soil profile, not just in the top half an inch or so of the soil profile, but it actually gets moved down deep into the soil, as deep as the roots go. So this is not what you might want to consider for a boron application, or perhaps you might. If you have a cover crop, and perhaps you want to move copper and zinc and manganese into the soil profile to a depth of 6-8 inches or more very quickly, then you can simply spray the cover crop with a very strong application of trace minerals a few days before terminating it or a few days before incorporating it. And you have this effect where it can move the trace mineral down through the soil profile very quickly and very effectively. So you can actually move trace minerals through the soil and not just have them be on the leaf surface, by using the plants as a vehicle to move them down a bit more deeply. When we look at zinc, zinc is the one trace mineral metal that doesn't exist in the soil in different oxidation states. So it is the one trace mineral that I'm most comfortable, and we see the biggest responses, crop responses from soil applications. So soil reports are generally accurate. They correlate with what the plants are telling us. The tissue analysis is somewhat accurate as well, at least in terms of measured zinc absorption from the soil. And sap analysis, again, is very accurate. I actually think, so in mainstream production agriculture, zinc is the one trace mineral that is widely used. It's applied in furrow when planting corn. It's often foliar applied. And it is the one trace mineral. The reason it's so widely used is because it is the trace mineral that has been the most documented as providing a yield response, which is a bit crazy because manganese, if anything, gives an even bigger yield response than zinc does. Copper and boron also provide significant yield responses. I believe the reason zinc has been the one trace mineral that has really been focused on by mainstream agronomy is because it is the trace mineral that works even in compromised soils with compromised biology. It's the one trace mineral that doesn't have different oxidation states. If the same degree of research was done with the reduced and chelated form of manganese, manganese would also be equally widely used as zinc. But it's not, because it needs to be managed a bit more carefully than zinc does. We are very comfortable making recommendations for zinc as a soil application in the form of zinc sulfate. From a distribution perspective, we again prefer to see sprayed on rather than broadcast. And foliar applications are also very effective as long as they are chelated. And again, the reason for chelation in this case is not to change the oxidation state or stabilize the oxidation state, but to have efficient absorption and translocation within the plant once it is absorbed. So as I mentioned when I was speaking about iron, it's important to think about the types of laboratory testing that you need to accurately document deficiencies if you're seeking to be organically certified. Another point to make is that naturally derived sources of trace minerals, such as rock powders and such as compost, seldom contain high enough concentrations of these trace minerals to correct soil deficiencies. And I'm referring in this context specifically to zinc and manganese and copper. Actually, copper is an exception. In livestock environments where copper is used as a foot treatment or as a dip treatment, it is sometimes possible to find compost that has very high copper levels, high enough that they can become a problem actually. So in some contexts, we can find these more natural type materials that contain higher concentrations of copper. But usually, we should not think of rock powders, for example, and mined rock materials, as changing the levels of zinc, manganese, copper, cobalt in the soil profile. They may supply adequate levels of the ultra trace elements, such as selenium and nickel, that are required in fractions of a part per million. They may be able to supply some of those elements, but usually they're not able to supply adequate levels of zinc, manganese, iron, and so forth. Those really need to come from our soil geological profile or from the more purified forms of trace minerals that we add directly until we get soil biology releasing what is in our soil mineral matrix. Many of you are familiar with our rebound trace mineral lines. They are developed so as to be in the reduced oxidation state for all the minerals for which that is appropriate, and to be chelated with organic chelation agents that provide for efficient absorption and translocation within the plant and show good results based on sap analysis performance. So those are the thoughts that I want to share. I'm going to switch to Q&A. I've seen lots of questions coming in. Thank you for those. First question from Charles Bergeron. Hi, John. We have sandy soils with about 5,500 pounds per acre calcium. In calcareous soils, are we further reducing micronutrient availability in the soil by applying more calcium, such as gypsum at planting, and chelated calcium in the irrigation/foliar? Or do plants in calcareous soils still benefit from these types of calcium applications if microbial activity is not optimal? Charles, this is an awesome question. And the answer to your question is no. Additional calcium applications, such as gypsum, will not further reduce trace mineral availability, because your reduced trace mineral availability in calcareous soils is coming as a result of oxidation, which limestone is very effective. It's a very effective oxidizer. And the reason for that is because of the carbonate component. So it's CaCO3. It's those three elements of oxygen that are in the carbonate that have the oxidizing effect. So it's not the calcium that has the oxidizing effect. Instead, it is the carbonate. So when you look at gypsum, calcium sulfate, you do also have the presence of oxygen in sulfate form. But when you look at the quantities of oxygen applied, they're comparatively small in gypsum as compared to limestone. And so you do not have nearly the oxidizing effect with gypsum that you do with limestone. And I would highly recommend using it in calcareous soils if you need a fertilizer grade calcium. Another question here from Skip LaCroix, Southwest Missouri. I have 84% calcium on my Logan Labs soil test. Basically, I have soil made of limestone. Is there a point in trying to amend these soils, or should I just bring in soil? And what would be a good starting point? So this is for small scale for gardening. The answer is yes, you can amend your soils, and you can amend your soils as you increase organic matter. Your organic matter should have a significant cation exchange capacity. And as organic matter increases, your 84% calcium can drop down to 60 to 65% calcium as you increase your CEC. And of course, I don't know the rest of the context. It's not enough to look at calcium just purely as a percentage number, because if it's 84% on sandy soil and it represents 500 parts per million, it's still not enough. So there's more to be considered there. But in general, you can increase cation exchange capacity and reduce your calcium percentage within reason. And I know that you're in Missouri and not somewhere in North Dakota where we have 40 CEC soil, so I'm comfortable making that comment. Question from Jesus: does acid extraction of humic deposits maintain the high anion exchange capacity needed to keep the boron in the soil? I'm not entirely certain. I know that it certainly damages it, and my understanding is that the human fraction is the fraction that best complexes boron and holds it stable, but fulvic acids do as well. And you may notice that I just used the word different from chelation. I used the word complexing. In scientifically correct terminology, chelation is only used to refer to cations, positively charged minerals. And when we talk about anions, such as boron, the term that is used is complexing. Slightly different terminology describing, in at least in practical terms, the same types of reactions and mechanisms that we're looking for. Question from Ito. Hi, Ito. It is thought that copper has some toxicity in stone fruit. Can copper be sprayed on stone fruit crops to reduce fruit cracking? Ito, the answer is yes. The difference is in the formulation and how it is used. So there's a difference between copper, chelated copper as a nutrient, and copper as a bactericide. The copper that is formulated as a bactericide is formulated to remain on the leaf surface and to kill the living organisms that are present on the leaf surface, where copper as a nutrient is intended to be absorbed by the plant, and once it is inside the plant and in the fruit, in the case that you're asking of fruit skin, one of the things that copper is known for is to provide elasticity. So limbs and stems become more flexible, they don't break off as easily, and skin also becomes more elastic and doesn't crack quite as easily. Question: what do you think about copper chelated with heptagluconic acid? I don't have experience, so I don't know. That is obviously an organic type of chelation agent, so I would suspect that it will probably be absorbed by the plant well, but perhaps not translocated so well, depending on how rapidly the plant uses that compound. And again, I don't have experience with it, so I really don't know. Question from Ryan Newton: can you speak to the effectiveness of fertigation of chelated nutrients, especially the ones that are susceptible to oxidation? What we have observed is that as long as they are chelated well, then fertigation is fine. They are absorbed by the plants very effectively. Question from Niels Korfeld. Hi, Niels. What is the correct oxidation state of iron? The correct is in the reduced form, which is in, I get these mixed up all the time. I know which it is, but it's one of those things that I get confused on. I think it is a double positive, Fe++. Not entirely certain of that, though, so Wikipedia will tell you the answer for sure. Question from Steve. In a rotational grazing system, when should we aim to apply our foliar applications, in front of or behind the mob? How many days behind our head, assuming a 40-day rotation? You want to time your foliar applications when the plant is most able to take advantage of it. So that usually means when you have 2 to 3 inches, 3 to 4 inches of regrowth. So at that stage, your foliar application produces the biggest crop response, the biggest forage response, because the plant has the most time to take advantage of it to increase its photosynthesis. Question from Andrew Johnson: are animals and humans able to use the oxidized forms of micronutrients in plants? That's a good question, and I don't know the answer. It probably varies between ruminants and monogastric animals and birds. A ruminant animal has a fermentation vat called the rumen, which is anaerobic and reduced by design. So there's a good probability that anything, I would guess, I don't know this answer for sure, but I would think it's reasonable to guess that whatever is absorbed, even in the oxidized form, is probably converted to the reduced form in the rumen. Is that also true of the microbiome in the digestive tract of a monogastric animal such as ourselves? I don't know the answer to that, perhaps. Just a further comment on that. When we think about human health, it's important to recognize that within human health and nutrition, we use different terminology, or animal health for that matter. We use different terminology to talk about exactly the same thing. So we have oxidation versus reduction, aerobic versus anaerobic, oxidants versus antioxidants. So vitamin C as an antioxidant is simply a very strong reducing agent, as are all these other antioxidants such as resveratrol and anthocyanins and so forth. When you stand on the ground in your bare feet and you earth yourself, that earthing, that grounding, is a flow of electrons that is the equivalent. Has a very strong reducing effect. So there is biophysics terminology and biochemistry terminology that both refer to the exact same processes, but they use different words to describe the same thing. Question from Barbara. After approximately 20 years of applying Solubor, we are seeing sodium building up in the soil. How do we safely apply boric acid? First, I would be incredibly surprised if you are seeing sodium building up coming from the Solubor. I would guess it's probably coming from other places, because the quantity of sodium that you're applying in Solubor is so small that most plants will absorb it and use it and remove it, and it won't, or even if it cycles within the local environment, it's still extremely small. It's more probable that it's coming from compost, from ruminant animals that are supplemented with sodium. That would be my first guess of where the sodium is coming from. Then your follow-up question is, how do we safely apply boric acid? It's going to be more work to dissolve it and get it solubilized in water, but it's still possible. So you need to use hot water and solubilize it and apply it in that form. Question from Dejan. I'm asking you to give general recommendations for every phenological stage for foliar applications of boron, cobalt, copper, iron, and manganese. It's a good question, and I've already given that webinar. So that information is already out there in the webinar that was just a few months ago, titled Managing Nutrition at Critical Points of Influence. A question on what kind of iron fertilizer is the most soluble. These are questions coming from overseas. Growers here in the United States have not just in the US, but also Mexico and Canada, here in North America, have the opportunity and the privilege of being able to easily access the AEA rebound liquid trace minerals, which are reduced and which are chelated. Producing those types of materials on your own is not impossible, but difficult and challenging, and something probably that most people don't want to attempt. So there's lots of questions here coming up in the Q&A from people who want to access these types of materials locally. And I don't know what companies and what resources are available overseas for you to find these types of materials. That will require research on your part to see what you can find. And I'm sorry that I can't give you better information on that. Question from Barbara. In the past, you've recommended including molybdenum with all nitrogen applications. Would this create an excess of molybdenum that would have a negative impact on the availability of other nutrients? We've never observed this to be the case. The question, of course, is what is the application rate that you're applying? So if you're applying in excess, then you will accumulate in excess, but we haven't observed that to be the case in our experience. Question from Derek, is there a best time of day or other conditions for foliar applications? Yes, I have answered this question also in some detail in the webinar on how to properly design a foliar application, and the answer is in the evening is usually the best for most growing conditions in most contexts. Question, after greenhouse soil gets sterilized by steam, it suddenly has substantial availability of manganese, shown on soil analysis as well as in sap analysis. Whereas before soil sterilization, it shows nearly deficient. Any thoughts on what the mechanism is or how this is possible? Yeah, it's fairly easy, actually. The microbial population will accumulate, they will extract manganese from the soil mineral matrix and hold them within their microbial cells. Then when you sterilize that soil with steam, you kill all the biology, and all of the manganese contained within those microbial cells is now available for plant absorption. So that's where it's coming from. Question from Steve, can I explain water hydrolysis further? How much of the plant's water requirement is involved in water hydrolysis? So this is the context for this question is that in other webinars I've described the function of manganese and needing to be present for water hydrolysis to split the water molecule into H and OH for the photosynthesis process. And this final question is, if manganese is lacking, is the plant's water efficiency reduced or the overall productivity of the plant diminished or both? The answer in my understanding is both. You both slow down the photosynthesis process, and as a result of the slowed photosynthesis process, you have increased photorespiration, which requires more water, of course, which lowers the water use efficiency, and which also has a drag on plant yield and has a yield drag effect. Question about silicon. There's a few thoughts on silicon. I'll just share them briefly. One is, like iron, there's abundant silicon in the Earth's crust, about 23%. And what we've observed on sap analysis is that there is a direct correlation between microbial activity and silicon absorption. When we have really good microbial activity, silicon levels go up. This is such a direct effect, such a direct correlation that we can actually use silicon absorption as an analog measurement for the health of the soil's microbial population, the soil's microbial community. Question, are you familiar with chestnut gall wasp? Can it be controlled with nutrition? What about the olive fruit fly? The answer is, I'm not familiar with them. And even though I'm not familiar with them, I'm confident that they can be controlled with nutrition because we have never yet discovered any insect or any pest anywhere that cannot be effectively managed with nutrition, including locusts. Question from Bart Van Andel. Hi, Bart. Does copper sprayed onto tomatoes for disease control distort the copper levels in sap analysis? Our experience has been no. That has not been the case. The same is true of manganese and zinc. When we have fungicidal or bactericidal type applications of Maneb or Mancozeb or Zaneb, these various different types of zinc and manganese and copper formulations on the leaf surface, I can't say definitively that they never impact sap analysis reports, but I do know a number of situations where growers were applying significant amounts of these types of applications, and the sap analysis would actually show that these nutrients were deficient. The same has been true of sulfur. When growers have applied powdered sulfur or sprayed sulfur onto the plant, in a number of cases, the sap analysis comes back and shows a sulfur deficiency. Now, that isn't always the case. Sometimes they do show high as well. We haven't looked at this extremely closely, and I can't say definitively that they never show up. But I do know that there are cases where they actually show up as being deficient when these types of compounds are being applied. There's a question here from Greg on our experience with sea minerals from ocean water. Can these ocean minerals improve the trace minerals? And the answer is not directly. Ocean minerals themselves don't contain appreciable quantities of zinc, manganese, iron, copper, and so forth. Now, they can indirectly, by stimulating the plant or by stimulating soil biology. Sometimes it's not uncommon for us to put on a foliar application of one trace mineral and see all of them respond. For example, cobalt is a good example. When sap analysis might show that we have moderate to low levels of zinc and manganese and iron within a plant and very low levels of cobalt, we'll put on a foliar application that perhaps because of the crop or the context, maybe we don't include all those trace minerals, but we do include cobalt. And all of a sudden, zinc, manganese, copper, iron levels will jump by 30 to 50%, and we didn't put on any. So it is possible indirectly to influence these trace minerals as a result of improving the soil's microbial population and improving overall plant health. But the ocean minerals themselves don't contain any significant quantities of trace minerals. Question from Darren. I have 263 parts per million bicarbonates in my irrigation water. How impactful will this be to trace mineral availability? And is it safe to assume the worst impact will be on elements that we require in the reduced form? Darren, this is an awesome question. The answer is that yes, it will be very impactful on trace mineral availability. Also, yes, it will be the most impactful on the elements that are required in the reduced form. However, broader than that, it will also have kind of this overarching umbrella dampening effect on on mineral availability in general, not just trace minerals, but also calcium, magnesium, and phosphorus, and so forth, because of its effect on suppressing the microbial population. So when we have these high bicarbonate content irrigation waters, then it can really suppress microbial activity, which has a very suppressive effect on just general across the board mineral availability in addition to trace minerals. That's a very good question. Question from Lori Brown. What are the best ways or products or microbes to reduce manganese in the soil and make it available to plants? Foliar is good, but not always possible. Lori, this is a very important question and a very good question. In fact, it's so good that I think we're going to have a separate webinar specifically around that, because this is also a question I've been getting asked a lot, and it deserves an in-depth answer. The simple, kind of the bullet point answer is that you need to grow cover crops which have a symbiotic microbial community that is strongly reducing. The top of the list, kind of the king of the mountain, are oats and buckwheat. So start there, and then we'll have a detailed webinar where we focus on that topic specifically, because it is a broad area that needs to be discussed and that needs an in-depth conversation to really make sense of. Question from Johannes Bacher. Is there an element or mineral important to suppressing damaging nematodes and flower bulbs? The answer is yes, it's molybdenum. In combination, high applications of humic acid, strong applications of molybdenum, generous applications of ocean minerals. The combination of those three seems, in all the experience that I've had so far, has been very effective against nematodes of any type in any crop. Has not failed yet, and it's been used quite widely. So that is the place where I would begin. Question from Philip Shorall. In general, is it a good idea to apply seaweed foliar applications for vegetable crops? The answer is yes. We include it in everything that we do, in every application. It's, for many growers, it's become a standard. It goes into every tank mix. Niels Korf, what's a safe level of liquid calcium to be applied with worm liquids? I'm assuming you are referring to worm tea, compost tea, or compost extract for transplant drenches and field applications without a test. What forms of calcium would these be? Definitely avoid calcium nitrate. I would calcium sulfate or a calcium suspension of some type, similar to AEA's HoloCal, would be the types of materials that I would look for. If we can't do sap analysis in the lab, could we use strict test kit for micronutrients from petiole extraction? The answer is no. There is no replacement for sap analysis in the lab. Nothing comes close. Not a refractometer, not strip tests, not the Hariba meters. Sorry, I don't have a better answer for you, but there is just no, in terms of agronomic integrity and scientific integrity and making good recommendations that actually work, there is no replacement for sap analysis. Question from Gary Nicely. Hi, Gary. Is there any disease and insect susceptibility that you might expect with a calcium and boron excess? I've not encountered that often enough that I have enough experience to comment, Gary. I can think of two situations where we did experience that. Both were on strawberries, one on the East Coast and one on the West Coast, but there were not any particular patterns of pest susceptibility. There was slowed growth, but that's the only thing that we really observed. So I'd be happy to dig into that a little bit more deeply with you in a follow-up conversation. There's a question, what is your take on EDTA chelated micronutrients for foliar and fertigation? And I was actually going to speak to this and missed it. I am not a fan of synthetic chelation agents, particularly EDTA, principally for the unintended consequences or the second order consequences of these synthetic chelation agents. In some cases, we speak about chelation as being a good thing, and some cases about chelation as being a bad thing. In the case of glyphosate, for example, or many herbicides, we have very powerful chelation agents that are so strong they have the capacity to kill plants. That's obviously not a good thing in living systems. And then you have chelation where you have microbial populations in the soil, extracting minerals and chelating them with organic acids and amino acids, making them available for plant absorption. That's obviously a good thing. What is the difference between the two? The difference is the chelation bond strength. So glyphosate and other herbicides have an extremely strong chelation coefficient, and the organic and amino acids have a much weaker chelation coefficient. EDTA and these synthetic chelation agents are in the middle. They're between those two opposite ends of the spectrum. The challenge is that when you apply an EDTA chelate of, let's say, manganese or calcium or iron, then when the chelate releases the ion that it is attached to, an iron or manganese ion, for example, it then picks up something else from the plant and chelates it, and it will actually extract it out of plant tissue. That could be calcium, could be iron, it could be cobalt, could be any one of, it will be whatever is in closest proximity that the plant has the highest chelation coefficient for. So it is possible to apply EDTA chelates and actually induce or amplify and increase trace mineral deficiencies of trace minerals other than the one that you applied. And in some cases, when larger quantities of EDTA chelates are supplied, it's even possible to induce a calcium deficiency. I've actually observed that to be true. So in general, I prefer to avoid the synthetic chelation agents. So I want to say thank you to all of you for attending. I hope that you found the information useful and valuable. Have a wonderful growing season, and we'll talk to you again soon. Have an enjoyable day.